हेलो दोस्तों, वेलकम टू पायोज एकेडमी। आज के इस वीडियो में हम कंट्रोल वॉल साइजिंग के कुछ इंपॉर्टेंट इंटरव्यू क्वेश्चंस डिस्कस करने वाले हैं। तो चलो हम इस वीडियो को स्टार्ट करते हैं।
Payos. Learn the smarter way.
When you are asked to size a control valve, how do you approach the problem from a process perspective? And which standards do you follow?
When I'm asked to size a control wall, my first step is to understand the control objective and overall process intent. I confirm what variable is being controlled: flow, pressure, level, or temperature, and how critical that control is to safety and operation. Then I define all operating cases: minimum, normal, and maximum flow, because a wall must perform over the entire operating range, not at just design flow. For sizing methodology, I strictly follow IEC 60534 and ISA S75 standards, which are industry accepted for control wall sizing. These standards give equations, correction factors, and limits for liquids, gases, and vapors, including cavitation, flashing, and choke flow checks. I also refer to vendor manuals like Fisher, Samson, or Masonillan for practical interpretation, but IEC and ISA remain my best standards.
What exactly does control valve CV represent physically? And how is it different from line hydraulic capacity?
CV represents the flow capacity of a wall, not the line. Physically, CV is defined as the number of US gallons per minute of water at 60 degrees Fahrenheit that will flow through a wall with a pressure drop of 1 psi. In simple terms, it indicates how easily a fluid can pass through the wall opening. This is different from line hydraulic capacity because piping capacity depends on pipe diameter, length, roughness, and fittings, while CV depends on wall geometry and trim. Even if the pipeline can carry a certain flow, the control wall may restrict it if CV is insufficient. That's why wall sizing and line sizing must be treated as two separate hydraulic problems.
Do you size a control valve based only on normal flow? Why do you consider minimum and maximum flow cases?
No, sizing a control wall based on only normal flow is a common mistake. I always consider minimum, normal, and maximum flow cases. Minimum flow ensures the wall can control without falling below its controllable range, avoiding stinction and poor resolution. Maximum flow ensures the wall does not saturate at full opening and still maintains control margin. If a wall is sized only for normal flow, it may end up oversized or undersized under off-design conditions, leading to hunting, instability, or inability to meet process demand. Good control design always accounts for full operating envelope.
How do you decide the allowable pressure drop across a control valve? And what happens if this is chosen incorrectly?
Allowable pressure drop is a design decision based on wall authority and system hydraulics. Typically, I ensure the control wall takes reasonable portion of total pressure drop, so it has sufficient authority over the system. If the pressure drop is too low, the wall becomes insensitive and control quality degrades. If it's too high, it leads to energy loss, noise, cavitation, or flashing. An incorrectly chosen pressure drop can cause either poor controllability or long-term mechanical damage. So, I balance controllability, energy efficiency, and equipment protection.
Between minimum, normal, and maximum flow cases, in which case is the valve pressure drop typically highest? And why?
Typically, the pressure drop across a control wall is highest at minimum flow conditions. At low flow, the wall is more closed, creating higher restrictions which increases pressure drop. At maximum flow, the wall is more open and pressure drop is usually lower. This is why minimum flow cases are critical for checking cavitation, flashing, and controllability, even though many engineers focus only on maximum flow.
What is valve authority? And how does it affect loop stability and control quality?
Wall authority is the ratio of pressure drop across the control wall to the total pressure drop of the system. It indicates how much influence the control wall has over the process. High wall authority means the wall has strong control over the system, leading to stable and predictable control. Low wall authority means most of the pressure drop occurs elsewhere in the system. So, small wall movement have little effect, causing sluggish or unstable control. Good wall authority is essential for responsive and stable control loops.
What problems do you expect if valve authority is very low?
If wall authority is very low, the control loop becomes difficult to tune. The wall responds slowly to controller output, leading to oscillations, overshoot, and hunting. Operators often try to compensate by aggressive tuning, which further destabilizes the loop. In extreme cases, the wall appears to be moving, but process variable hardly responds. This often results in complaints that the control valve is not working, when in reality the problem lies in poor hydraulic design.
Why is operating a control valve around 60 to 80% opening considered good engineering practice?
Operating a control valve between 60 and 80% opening gives the best balance between controllability, stability, and future flexibility. In this range, the valve trim is well engaged, so small changes in valve position result in predictable changes in the flow. If a valve operates mostly below 30% opening, it becomes very sensitive. Small movements causes large flow changes, leading to hunting and poor control. On the other hand, if it operates near 100% opening, it loses control authority and cannot respond effectively to the disturbances. Keeping the normal operating point around 60 to 80% also provides margin for future capacity increase and accommodate variations in process conditions without replacing the wall.
If you notice a valve consistently operating at 20 to 30% opening, what conclusions would you draw?
If a control valve is operating mostly in the 20 to 30% opening range, it usually means the valve is oversized relative to the process. At low openings, the valve is extremely sensitive. Small changes in actuator position causes disproportionately large changes in the flow. This leads to hunting, oscillations, and poor loop stability. In addition, operating so far from the best efficiency point can cause noise, vibration, and premature trim wear. From a process perspective, this is a red flag for either wall oversizing or poor pressure drop allocation in the system.
Smaller pressure drop results in a larger control valve. Do you agree with this statement? Explain.
Yes, this statement is true. For a given flow rate, if the allowable pressure drop across the wall is small, the wall must provide less resistance, which means a larger CV is required. A larger CV translates to a larger wall size or wall with higher capacity trim. Conversely, if a higher pressure drop is available, a smaller wall can achieve the same flow. That's why pressure drop allocation is a critical decision in wall sizing. It directly affects wall size, cost, and controllability.
Can you explain the difference between inherent and installed characteristics of a control valve?
Inherent characteristics describe how the wall flow changes with wall opening under constant pressure drop conditions. Common inherent characteristics include linear, equal percentage, and quick opening. However, installed characteristics describe the actual behavior of the wall when installed in a real system, where pressure drop varies with the flow. Because system resistance changes, the installed characteristic often deviate significantly from the inherent ones. As a process engineer, I focus more on installed characteristics because they reflect how the wall will actually perform in operation, not just on paper.
How do you decide between linear, equal percentage, and quick opening trim characteristics?
The choice of trim characteristic depend on how the process gain changes with the flow. A linear characteristic is suitable when the system is fairly linear, meaning flow change is proportional to wall opening, which is rare but sometimes used in simple flow loops. Equal percentage trims are most common in industrial processes because they provide small changes at low opening and larger changes at high openings, which matches many process gain curves and gives better stability. Quick opening trims are used mainly for on-off services or when you need rapid initial flow increase. In practice, I analyze the process curve, consider controller gain, and select the trim that gives stable control over the full operating range.
What factors guide your selection between globe, ball, and butterfly control valves?
Wall type selection is guided by throttling precision, size, cost, pressure rating, and flow type. Globe valves are preferred for precise throttling and where good control across a wide range is required. Ball valves provide fast operation, low pressure drop, and compact design, but their control is less precise at low openings. Butterfly valves are lightweight, low cost, and used in large diameter, low precision flows, but they may produce more non-linear response. Other factors include cavitation tolerance, maintenance accessibility, and material compatibility.
If an existing globe control valve is replaced with a ball or butterfly valve, what changes would you expect in control behavior?
Replacing a globe wall with a ball or butterfly wall typically reduces control resolution and loop stability, especially at low openings. The inherent characteristic of a ball wall or butterfly wall is less linear, so small changes in actuator movement can lead to abrupt flow changes. You may also see increased overshoot or hunting, and in some cases, the process may require retuning of the controller to maintain stable operation.
What is meant by control valve shutoff? And where's tight shutoff really required?
Control valve shutoff is the ability of the valve to stop flow completely when closed, usually defined by leakage class according to IEC 60534 or ANSI standards. Tight shutoff is required where leakage can cause a safety hazard, product loss, or process upset, such as in fuel systems, toxic chemicals, high pressure steam, or vacuum applications. For non-critical service, a standard leakage class may be acceptable.
What is cavitation in control valves? And how is it different from flashing?
Cavitation occurs when local pressure in the wall drops below the liquid vapor pressure, forming vapor bubbles that collapse downstream. This causes high velocity jets, vibration, noise, and severe trim damage. Flashing occurs when pressure drops below vapor pressure but remains below in downstream, so bubbles do not collapse. Flashing causes erosion rather than impact damage. Cavitation is more aggressive and damaging phenomena than flashing.
During sizing, how do you identify whether cavitation or flashing will occur?
I calculate the pressure drop across the wall and compare it with vapor pressure of the liquid at operating temperature. Using IEC 60534 cavitation index and the pressure recovery factor FL, I can predict whether the flow will cavitate or flash. If delta P across the wall exceeds the allowable limit for the service or outlet pressure is below vapor pressure, then cavitation or flashing is expected. Vendors often provide charts or software for these checks.
If flashing or cavitation is predicted, what practical solutions would you consider?
Depending on the severity, I consider anti-cavitation trims, multi-stage walls, pressure drop redistribution, or using a different wall type. Sometimes the operating point can be adjusted to reduce delta P or process can be modified to increase downstream pressure. Material selection and trim design also play a role in minimizing damage from high velocity jets.
What is choked flow in a control valve? And does it occur in liquid service, gas service, or both?
Choke flow occurs mainly in gas or vapor service when the flow reaches sonic velocity at the vena contracta, meaning further reduction in downstream pressure doesn't increase flow. In liquids, the term is not commonly used, but similar behavior is observed if cavitation causes flow limitation. Choke flow limits the wall effective CV and must be accounted for in high pressure gas systems.
How does an increase or decrease in downstream pressure affect control valve performance?
An increase in downstream pressure reduces the differential pressure across the wall, which reduces the flow for the same wall opening. Conversely, a decrease in downstream pressure increases the differential pressure across the wall, which may cause higher than intended flow, along with cavitation or flashing in liquids and choke flow in gases. These pressure variations directly influence loop stability, controller tuning, and potential equipment damage, so they must be considered in sizing.
Apart from CV calculation, what additional checks do you perform for gas or vapor control valves?
For gases, I check choke flow, velocity limits, noise prediction, vibration, and pressure drop ratio. I also consider the Joule-Thomson effect, as high pressure drops can cause a significant cooling, potentially leading to condensation or material brittleness. These checks ensure safe and reliable operation beyond just flow capacity.
Can you explain the Joule-Thomson effect and its relevance in gas control valves?
The Joule-Thomson effect describes temperature change of gas during expansion at constant enthalpy. For most gases, at high pressure expansion through wall causes cooling. This is critical in cryogenic or high pressure gas walls because excessive cooling can lead to condensation, hydrate formation, or material embrittlement. During wall selection, I ensure wall can handle the expected temperature drop safely.
How do noise, velocity, and vibration influence gas valve selection?
Excessive gas velocity can cause erosion, noise, and vibration, which reduces wall and downstream piping life. I ensure outlet velocities are below recommended limits as per ISA or vendor data. Select noise attenuating trims if necessary and check for resonance frequencies to avoid vibration. Ignoring these can lead to failure and maintenance issues.
Can a control valve be used as a pressure safety device? Why or why not?
No, control valves cannot replace a pressure safety valve. Control valves are active devices dependent on power, signal, and actuators. PSVs are mechanical, independent, and fail-safe, designed to protect against overpressure automatically. Control valves can help reduce PSV duty but cannot serve as primary overprotection.
How do you decide whether a control valve should be fail open or fail closed?
Fail position is chosen based on process safety and fail-safe philosophy. For example, a cooling water valve may fail open to prevent overheating, while a fuel supply valve may fail closed to avoid fire. I always consult hazard studies and process risk assessment before finalizing the fail-safe position.
What would be the impact of changing an actuator from pneumatic to electric?
Electric actuators provide precise positioning and easier integration with digital controllers, but generally respond slower than pneumatic actuators and may require breakup power. Changing actuators can affect loop tuning, response time, and failsafe behavior. So, testing and controller adjustments are required after such a change.
When reviewing a vendor control valve datasheet, what are the critical parameters you always verify?
I verify CV, wall size, trim type, pressure rating, temperature rating, actuator sizing, leakage class, noise prediction, cavitation or flash prediction, and material compatibility. I also check assumptions used by the vendor against the process datasheet to ensure there are no mismatches before the approval of datasheet.
What happens if the selected control valve size is larger than the line size?
A wall larger than the pipeline will operate mostly at low opening percentages, causing instability, hunting, poor controllability, and actuator oversizing. It also increases initial cost without process benefit and may reduce loop responsiveness.
What are the typical operational issues caused by oversized control valves?
Oversized walls often causes hunting, oscillations, excessive sensitivity at low opening, poor controllability, and premature trim wear. Operators may struggle to maintain stable control and frequent adjustments can increase maintenance workload.
Based on your experience, what are the most common mistakes process engineers make while sizing or selecting control valves?
Based on my experience, common mistakes are ignoring minimum flow, oversizing or undersizing control wall, assuming fixed pressure drops, neglecting cavitation or flashing, relying blindly on vendor sizing, ignoring wall authority, selecting wrong trim characteristics, and improper failsafe or actuator choice. These mistakes often manifest during commissioning as unstable loops or excessive maintenance.
If you inherit a running plant with unstable control loops, what control valve related red flags would you look for first?
I would check wall sizing versus line size, operating point relative to CV, actuator type and responsiveness, pressure drop allocation, presence of cavitation or flashing, trim selection, and wall authority. I would also review control loop tuning and instrumentation to ensure the wall is not the limiting factor. Early identification of these issues often prevent prolonged instability and helps prioritize corrective actions. चलो, आज के इस वीडियो में हम यहीं पे रुकते हैं। अगर आपको कुछ भी डाउट है तो आप हमें कमेंट करके पूछ लीजिए। थैंक यू, ऑल द बेस्ट।
Payos. Learn the smarter way.